So we started chapter 5, and we covered the initial theory, and also we solved one numerical problem related to air cycle refrigeration system. So let's continue where we left. Let's do another problem. So here we have an air cooling system for a jet plane. Cockpit operates on simple cycles. So far we are solving simple cooling cycle. Okay. The schematic is shown here. The cockpit is to be maintained at 25 degrees Celsius. So let's first number from the start to the end. So air is entering from the ambient. It is first ramped, or in the diffuser, pressure and temperature will rise to 0.2. Then from 2 to 3 in the main compressor of a jet engine, further compression. Okay, from 2 to 3 there is further compression in the main compressor of that jet engine. A part of it is flowing towards the air conditioning system. Then from 3 to 4 there is cooling in a heat exchanger with that air at 0.2. Okay. Then 4 to 5, that is the process occurring in a turbine. Then 5 to 6 is what? Cooling or the refrigeration effect. Refrigeration process from 5 to 6 inside the cabin, right? Okay, these are the points. So now let's see what is given here. Or maybe we can draw TS also first. Okay, so that is the ambient pressure, P1, low pressure. P2, pressure increase in the diffuser. 1 to 2, ideal, isentropic. Then 2 to 3, another compression, isentropic. Then 3 to 4, isobaric, yes. Heat transfer in the heat exchanger or cooling of that air. Then 4 to 5, another isentropic. Expansion in a turbine. 4 to 5. 5 to 6 is the cooling effect or refrigeration effect. Here we have assumed all the processes as isentropic or isobaric. Now let's read what is given here. Now it is saying that the simple cycle, which is shown here, the cockpit is to be maintained at 25. What is that temperature? Which point? Cockpit is clear, where the pilot sits. That cabin is called cockpit. That temperature is to be maintained at 25. So what is that temperature? 1, 2, 3, 4, 5, 6. What do you think? Where is the cockpit in this system? Yes. So where is the Mr. Pilot here? So what is this temperature, this point? 5 or 6? Look here, air is coming, yes, 6. Air is leaving that air conditioner. Very cool if you touch right here. But from here till here, what is happening? It is heating up. So if this is 5, then this is 6. right? You're not sitting just in front of it. So from here till here, some heat is absorbed. So it means here this temperature is the average room temperature or that cabin temperature. So this is T6 given. Here it's also mentioned here. T625. The ambient air, where is ambient air? 1, 2, 3, 4, 5, 6. 1. Okay, so the ambient air pressure and temperature are, this is P1 and T1. P1, T1. Okay. The pressure ratio of the jet compressor. Which process? Pressure ratio of the jet compressor. Pressure ratio of the jet compressor is 3. Here is the jet engine compressor. Pressure ratio means higher pressure divided by lower pressure. Pressure ratio. So P3 by P2 is given. 3. The plane's speed is 1000 kilometers per hour. So which point? Plane speed is 1000 kilometer. Plane is moving at 1000 kilometer per hour and air is entering like this. So where is this point? Where is this velocity? Before this, point 1. Velocity with which the air is entering. Not entering. The plane speed is 1000 kilometers per hour. So it means air entering into the air, into the airplane is at this speed, 1000 kilometers per hour. The pressure drop through the cooler coil. Which process? Pressure drop in the cooler coil is 0.1 bar. Where is it? Yes, 3 to 4. So it means it's not isobaric. So it means 0.4, from 3 to 4, there is a pressure drop. So 0.4 is actually here. So we need to correct it, initial assumption. So this is 0.3 pressure. So here we will have 0.4 pressure. So there is a pressure drop. From 3 to 4. This is P3. This is P4. It means P3 minus P4 is given. Higher pressure minus low pressure. The pressure of the air leaving the cooling turbine is 1.06 bar. Leaving the cooling turbine. Which point? 5, right. That pressure is given. And that in the cockpit is 1.013 bar, which is this 6. So it means from 5 to 6 again there is some pressure drop. Look here, it is 1.06, there is 1.01. So again some pressure drop is mentioned. So this is 0.6. So let's correct this 0.6 also. This is 0.5. There is a little, very little pressure drop from 5 to 6. Look, 0.6 pressure is higher than 0.1. 0.1 was very low, 0.325. So it's better to show it a little more above. Okay, but in any case, 0.6 pressure is higher than 0.1. Be careful about these things in exam. Okay, test 2 will be tough because of this. You have to read it properly and draw it properly. Any mistake here will make everything wrong. Okay. Now, what is given? The cockpit cooling load is 58.05. I don't know what is the meaning of 0.05 here. 58 kilowatts. Okay, so here is that cooling load. The amount of heat which is to be absorbed, right? Calculate the stagnation. Now we need to calculate stagnation temperature and pressure. If you have gone through the previous lecture video, then you know what is this. If not, then I have to explain a little bit here. Stagnation temperature and pressure of the air entering the compressor. Where is the entry of the compressor? Point, which point? Point 2, yes. So we need to calculate this point 2 temperature and pressure are known as stagnation. Why stagnation? When highest or yes, it is highest also, but the why we are using the term stagnant. What is meant by stagnant?
We took
Not moving.
in fluid mechanics stagnation acceleration.
Stagnation is something where something comes to a stop.
Yes, for stagnation there is the other thing. I don't.
Yeah, something. So in the diffuser, what is the purpose of a diffuser? Is to drop the velocity and increase the pressure. Right. So in the diffuser, what is happening? High velocity, 1,000 kilometer per hour. Now it reduces. So it reduces to such a small value. We say it almost becomes zero velocity from 1,000 kilometers per hour to very low velocity. So that point at the exit of diffuser is called stagnation. It is still moving with some velocity, but that change in velocity is so huge that we can say it has become stagnant.
Relatively, there is zero.
And we will be assuming zero velocity. Okay. So it means stagnation temperature and pressure at the exit of diffuser, point 2, not 3. 3 is at exit of compressor. Okay. So this is part A. Then part B is to calculate the mass flow rate of the air, which is flowing in this refrigeration system. Okay. Volume handled by compressor and expander. What is expander? Turbine. Another name of expander is turbine. Okay. And COP of the system. So let's start with part A. Part A, we derived an equation for that diffuser part in this form. T2 by T1 is equal to, there was an equation which we derived in terms of Cp or in terms of velocity of air. What was that equation? I do not remember. This was the equation which we derived for a diffuser. If we apply energy balance on the diffuser part, in the diffuser, the change in kinetic energy is not negligible. And so then we get this equation. Just see the theory. Okay. So we have this equation.
So C is the velocity.
C is the velocity. Cp is the specific heat of air. Okay. So derivation is there in the theory, which we covered last time. Okay. So this equation can be used to find out T1, T2, stagnation temperature. T1 is given. Velocity is given in what units? Kilometers per hour. So converted. So this will be 1,000 multiplied by 1,000 meters. Now per hour must be converted to seconds.
361.
So now this will be velocity, the c square term. I'm talking about this c square term. This will be in meter per second because there is square, so it will be meter square per second square. In other words, c is in meter per second. What is CP? Specific heat of air. Normally it is given as 1.005. We take it as 1.005 kilojoules per kilogram per Kelvin. But here we have, in the numerator, we have meters square per second square. That's what we did in thermo. I don't know if you remember. This term is not, okay, here kilograms per kilogram. What this becomes? Kilogram meter per second square Newton, Newton meter joules. Actually, this term is representing joules per kilogram. In the denominator, we have kilojoules per kilogram. So here you have to multiply with in the denominator. In the numerator, we have this term in meter per second square divided by 2 into Cp, but you have to multiply with 1000 because here we have kilojoules per kilogram. So by doing these unit conversions, here is the final T2. This is C in meter per second, C square divided by 2Cp multiplied by 1000. So we get T2. That's what we needed to calculate. Stagnation temperature. Using this, we can also find out P2. Because this process 1 to 2 is isentropic, and we know this for isentropic. For isentropic process, this is the equation which we know. So from here we can find out P2. Okay, that was part A, to find out stagnation pressure and stagnation temperature. Next, I think we need to calculate m dot. For m dot, I can use this equation, just a similar equation which we used in chapter 2 to find out m dot of refrigerant. Q dot refrigeration is equal to m dot into which path or which process? Yes, m dot Cp into, where is the cooling effect? So it means T6 minus T5. And what is Q dot? That is given the total tons, I think. So from here we can find out m dot, but I need to know T5. T6 is given 25, this one. But T5 we need to calculate. Q dot is also given, right? So to find out T5 can be calculated from T4, and T4 from T3, and T3 from T2. So calculate all those temperatures. Just like in chapter 2 and 3, what we used to do, we calculate enthalpies at all points. So here calculate all temperatures. We already have T2, now we can find out T3. What is T3? How to find T3? Isentropic compression, so T3 by T2 is equal to so from here I can find out T3. What about T4? Is T4 given? No. After that heat exchanger, the temperature. It's not given. Then what we can do here? Look, this 1 to 2, 2 to 3, 3 to 4. 4 we want to find out. It's not given. This is a heat exchange process. Do you remember effectiveness of a heat exchanger? Anyone? From heat transfer? Actual heat transfer divided by maximum. So what is actual heat transfer? MCP T3 minus T4 from 3 to 4 divided by what is maximum possible? What is the maximum possible? Maximum possible, this heat is exchanged with this air. So it means 0.4 temperature becomes 0.2. So that is maximum possible. Okay. This effectiveness is also not given. So what we will do, we will assume it as 1. Maximum. If it is given, okay, use it. So now I can find out T4. This MCP will cancel with this one and find out T4. T3 and T2 we already calculated. So let's go back here. T3 is calculated using isentropic correlation for compressor. Here is T3. This is Kelvin always. And then T4 is assumed equal to T2. That this 0.4 temperature will become same for 100% effectiveness of a heat exchanger. If effectiveness is not given, or solve the heat exchanger part using heat transfer, but we are not doing it here. We should know the type of heat exchanger, flow rates, temperatures, then we can do it, which we are not doing here. So that is one assumption which is used here in this problem. Okay, any questions so far? Okay, so T4 is known. Now I can find out T5 using, oh yes, one more thing, P4 is less than P3 in this problem. P4 is less than P3. How less? That is given. P3 minus 0.1 bar. And what is P3? This pressure ratio is given, P3 by P2. So it means P3 is equal to 3 into P2 because this is given. Okay. So now we have P4 is equal to 1.61 bar because I need P4 divided by P5 is equal to T4 divided by T5. Now I can apply this equation to find out T5. But P4 is not equal to P3 in this problem. Okay. So here you will have the answer in Kelvin converted to Celsius if you want. So now T5 is known. Now we can find out m dot. All right. Q dot is equal to m dot Cp T6 minus T5. Okay. So m dot comes out to be, that is in kilowatts. So that's why answer will be in kilograms per second. If you want, you can convert it into kilograms per hour. 5,941 kilograms of air in 1 hour is required. Okay. What was the next part? Next part was, I think, to calculate the volume handled by compressor. That was the last part C, volume handled by compressor and expander or turbine. What is the volume handled by compressor?
Current.
Yes, entering or exit, that's the question.
And
In a compressor, where it will enter? Here or here?
no, the right one.
Yes, because as it flows, volume drops. So we need to calculate the volume handled by compressor. Which one? The higher one. Where is higher? At the entrance. Where is the entrance? Point 2. In this problem, here is that compressor. Inlet of compressor is 0.2. So it means we need to find out V2. How to calculate V2?
We have the temperature thing.
mRT2, because ideal gas divided by V2. That will be V2. M dot we already calculated. So because we have M dot, not M. So what will be the units of this volume? V dot. What is R?
3.1.
Mhm.
3.1.
For air? 287?
0.27.
0.287? What is 0.287? Oh, okay, 0.287. Yes, if you say pressure is in kilopascal, but I am saying pressure is in pascal. The units of R, PV is equal to MRT, C thermo 2 or thermo 1, why to use 287, when to use 0.287. If you are taking this pressure in kilopascal, then it is 0.287. If pressure is in pascal, then 287. Okay. What is pressure at point 2? Did we calculate pressure? Yes. No, we have P2, which we calculated, stagnation pressure. And that is in bars. So what is bar in pascals? 10 to the power 5. That will give you pascals. Okay. So if you are using pascals, then R for air will be 287, not 0.287. Here you see 287. Here are the units of R. Units of pressure in this R is pascal, so that's why 287. So mRT2 you already calculated, P2 known, so here is the volume handled. Because here mass flow rate you are taking in kilograms per hour, that's why answer is meter cubes per hour. What about turbine? Now here is a turbine. Where is the inlet? Where is the outlet? Yes, because from inlet to outlet volume increases. So volume handled by turbine, the higher one is at the exit. For compressor at the inlet, for turbine at the exit. So where is the exit of the turbine here? Exit of turbine. 0.5. So it means we need to find out V5. Okay. So R, MR, T5 over P5 will give us V5. M dot is given, so we'll get V dot. Okay. M dot already calculated. R again 287. T5 calculated. Here is T5. P5, what is P5? Also given 1.06 bar multiplied by 10 to the power 5. Okay, so here is that volume handled by expander or turbine. Okay, just put values and find out. Okay, this value is not written here. I forgot to write. Okay. So what is the last part? Last part is to calculate COP. So its Q is known, work of compressor. What is work of compressor?
It's from 2 to 3.
2 to 3, MCP T3 minus T2.
The Q was very effective.
Yes, that is already given. Cooling effect. So 0.32 is the
why volume 100 is the higher also temper-wise?
Volume handled by compressor. So what we should say, maximum one or the minimum one? When I say, what is the volume handled by a compressor? Or what is the volume handled by a turbine? The maximum one or the lower one?
And
Handled. Of course, volume is changing from inlet to outlet for both compressor and turbine. So I will go for the maximum one, maximum volume handled, because you will design this turbine from inlet to outlet, volume is increasing. So you should know what is the maximum volume so that you will make this turbine structure accordingly. Inlet we know, but from inlet to outlet volume is increasing. So whenever you see a turbine in reality, you will see at the start blades height is lower. As you move in this direction, blades height is increasing. If you see multi-stage turbines. Similarly in the compressor, from inlet to outlet, if it's a centrifugal compressor, you will see volume is dropping. But highest one is here. Maximum volume handled by a compressor is at the inlet. Yes.
it's like a design requirement.
It's a design requirement. Yes. Okay. Let's do another problem. Now in these problems, be careful about the statement. Carefully read the statement. Okay. Now here the situation is very different in this problem. Solution is very easy, but situation is very different. So when you read the statement, draw accordingly, then solve it. If you make a mistake in the drawing, everything will be wrong. So let's see here what is happening. An aircraft air conditioning unit receives its air from the jet engine compressor. Okay. So if I show it like this, if this is air conditioning unit, AC unit, it is receiving air from jet engine compressor. That's what is written here. It is receiving air from jet engine compressor. Okay. And it is receiving at what pressure? That is given 1.25 bar. If this is 1, this is 2. So this pressure P2 is given 1.25 bars. An aircraft air conditioning unit, this one, receives its air from jet engine compressor at a pressure of 0.25 bars. Means P2 is given. If I say this is P1 and this is P2. The atmospheric pressure and temperature are 0.2 and 237. Atmospheric. P1. There is a diffuser or not, nothing is mentioned. So we'll take it, this one as ambient. This P1 0.2 bars, sorry. And T1 237 Kelvin. The air conditioning, now it is explaining the air conditioning unit. Okay. The air conditioning unit consists of another compressor. So here you have another compressor. Okay, let me show it like this. The air conditioning unit consists of a compressor and turbine mounted on the same shaft, on one shaft. So there is a compressor, there is a turbine, both are mounted on one shaft. It was not like this in the previous question. Turbine and compressors were not on the same shaft. And you had only one compressor, jet engine compressor. Now here you have two compressors, one jet engine compressor, another compressor for air conditioning unit. Okay. And here, this air conditioning compressor and turbine, they are mounted on one shaft. The air coming into the unit is compressed. The air coming into this unit is compressed to a pressure P. Now it is compressed to a pressure P, cooled at constant pressure. Now it is cooled in some heat exchanger at constant pressure, same P, and expanded in the turbine. Now it is expanded in the turbine to a pressure of 1 bar. So here let's number it: 2, 3, 4, 5. Now what is written? And expanded in the turbine to a pressure of 1 bar and temperature 280 Kelvin. So what is this 1 bar and 280? T5 and P5. Okay. Assuming that all the processes are reversible, calculate this pressure P and temperature of the air at exit from the cooler, where it is this T4. So P3 is equal to P4, which we are calling it as P, is to be calculated, and T4. Okay. So now you can see this problem is simple but very different from the previous one. Okay, now let's draw TS diagram because this is not enough. This diagram is difficult to imagine where is isentropic, where is not isentropic. Okay, if you can remember, fine, but better to draw it, TS diagram. So starting from point 1, pressure P1, then P2, then another compressor P3, isentropic, another isentropic. 1 to 2, 2 to 3, then 3 to 4, isobaric cooling, 3 to some point 4, then 4 to 5, 1 bar, because this pressure is low, ambient, 0.2 bar. This pressure is higher. This temperature was also low. Okay, so that is not a very good drawing. Point 1 should have been shown here. Okay, so this is 0.5, for example. I'll show this 0.5 a little higher. Temperature and pressure are higher than this one. This is 0.5. And work of compressor is equal to work of turbine. This second compressor is getting the work from the turbine in this question. So we need to find out this P. So how to find this P? Now, look, work of turbine is equal to work of compressor. That is one equation we can write. Or maybe just find out all the unknown temperatures first. And then see how to find out this unknown pressure and whatever we want. Okay. So let's start from point 1. Point 1, temperature and pressure is given. Point 2, I can find out. Point 2, only pressure is given. I can find out temperature. Right? Because isentropic, T2 by T1. So I can find out this T2. Then T3. T2 or T3 by T2, another isentropic. P3 by P2 to the power gamma minus 1 over gamma. Here P3 is unknown.
Yes.
This P3 is unknown. So I can write an equation of T3 in terms of P, because pressure is unknown. Then 4 to 5, I can write another equation of T4 over T5 is equal to P4 over P5. So I will have another equation of T4 in terms of unknown P, same unknown P. P3 is equal to P4 is equal to P. So I have an equation of T3 in terms of P, T4 in terms of P. So now two unknowns here, two unknowns here. Let's write another equation. Work of compressor is equal to work of turbine. MCP delta T of compressor is equal to MCP delta T of turbine, and there you will have T4 and T3 in this equation. So replace them with this, with unknown P. So you will have only one P unknown in that equation. That's what we have. Okay, let's go to the solution. So this was the schematic of this problem. First compressor, jet engine compressor, a part of it is going to the air conditioning unit. This one is our air conditioning unit. Okay. So then we draw the TS diagram. Here I initially draw 4 to 5. 5 was almost same as 1. That's why I corrected it, because 0.5 temperature is higher than 0.1. Pressure is of course higher, but so this was not right. That's why I removed it. Okay. This is TS diagram. This is by mistake. This is not for this problem. I have to remove it. Okay. So now we calculated all unknown temperatures first. T2, then T3. But for T3, this is P3 is unknown, so I'll have T3 in terms of P. Okay. Similarly, T4 over T5. So I have another equation of T4 in terms of unknown P. Now I will use this one, because work of turbine 4 to 5 is equal to work of compressor 2 to 3. This one and this one, which is equal to Cp delta T, MCP delta T, work of turbine. M dot will cancel, so Cp is also same. We are not considering change in Cp in this chapter, so it's simply given by this. So just put values T4 in terms of P and T3 in terms of P. T5 and T2 are known. T5 is given, T2 we already calculated. So put it here and find out unknown P. All right. Once P is known, now I can find out T4 and T3. Just put it here to find out T4 and T3. But our requirement is to calculate that temperature at the exit of cooler and its pressure. Okay. Any question?
This is the drawing, the schematic.
Any?
The complexity is the schematic.
Yeah. Yes, you need to practice all these questions. So that's what we have discussed so far. Simple cooling system, schematic, and TS. But that question which we have solved, it was a bit different. There were two compressors, and the second compressor was mounted on the same shaft with turbine. And there are many other variations which we'll see in this chapter. But this is the main system which we have discussed so far, simple cooling system. There is no evaporative cooling in this entire system. It's all sensible cooling, right? And here you see isentropic and non-isentropic changes in compressor, that is turbine. What is this? 1 to 2 diffuser. Okay. For turbine and compressor, how we define isentropic efficiencies? For turbine, it was actual over isentropic. Actual is T4 minus T5, or H. MCP is cancelled now, that's why. T4 minus T5 over, here is the turbine.
T4 minus T4 plus.
Actual is T4 minus T5 dash, and isentropic is T4 minus T5. Okay, for a compressor, isentropic over, so T3 minus T2 isentropic divided by actual T3 dash minus T2. Here what we normally assume that 0.3 and 0.3 dash temperature is different. What about pressure? We consider same pressure. Both are at same pressure. Here also both are at same pressure, but temperature we assume different. We say it's different. But that is not the case in case of RAM. Here how we define isentropic efficiency, not in terms of temperature, but in terms of pressure. Here we say pressure is different. It should have raised to 0.2, but it has raised to lesser than 0.2. Because what is diffuser? Just a pipe and nothing else. So when the fluid is flowing through a pipe or a duct, due to friction, pressure drops. Ideal diffuser, we said no change in, no frictional change, no friction drop. Okay, so that's why in actual diffuser, the pressure will be lesser than the ideal one. So here pressure rises more, here pressure rises less. So how we'll define diffuser isentropic efficiency, or RAM air actual pressure, P2 dash minus P1 divided by minus P1. Although we'll not be using it, we'll not be solving any problem involving isentropic efficiency of diffuser. Okay, but these ones we will be using. Okay. Okay. Any questions? So that is clear, hopefully. So these are the isentropic efficiency of a RAM, isentropic efficiency of a compressor, and isentropic efficiency of a turbine. Now, another version of simple cooling system with evaporative cooling. What you see here another heat exchanger. So at the exit of this heat exchanger, we further cool it. Using what? Using some refrigerant which is evaporating. If you want lower temperatures. Okay, and then it is sent to a turbine. So now let's show it on TS diagram. Starting from point 1, point 2, then 2 to 3, then 3 to 4, then 4 to, it is 4 dash actually, 4 to further cooling at the same pressure, 4 dash. If we carry some coolant with us in that aircraft. Okay. What is the advantage? When there was no such evaporative cooler, after this there was a turbine. Now you have further cooled it, now there will be a turbine. So you can reduce this temperature further. It would have been here, now it is further dropped. That is the advantage if we need more cooling or more lower temperature. Okay, so now there will be a turbine from 4 dash to 5 dash, then 5 dash to 6 is what? Refrigeration effect. Okay, for example, there is a 10-hour flight. So for these 10 hours, we can calculate how much this fluid we should take for that flight. That in 10 hours, all of it will be evaporated and you got that cooling. It is, for example, you are taking cold water with you at some low pressure and it is evaporating. Right. So that is with evaporating. In some systems where we need lower temperatures, or maybe when this aeroplane is moving at a very high speed. Very high speed means you will have here T2 much higher. As this C increases, this stagnation temperature also increases. So this 0.2 would have been here, but now this is here because speed of the aircraft is so high. So here you have already very high temperature, so then that's why you need to drop this temperature more. So we use that extra evaporative cooler. Okay. Can we calculate the amount of mass of that evaporative cooler which we should take with us? Okay, let's write its equation. This evaporative cooler, what is it doing? It is absorbing heat from that air and getting evaporated. So I can write m dot is equal to, sorry, q dot, which is supplied to that fluid, is equal to m of that fluid into HFG of that fluid. The total amount of mass I want to calculate. What should be that m dot? That depends upon how much heat we want to remove. And it is evaporating, that's why it's not mCp delta T, it is m into HFG. But here it is dot, here it is m, so divided by time. So from here I can find out this m, how much mass I should put here. What is this q dot? Q dot I can calculate from here, m dot Cp4 minus 4 dash. This will give me q dot. HFG for whatever refrigerant I'm taking, I know it's HFG. What is the time here? If it is 20-hour flight, so 20 hours.
It's not the time of the evaporation.
Time of the evaporation, but how long? So it is the total flight time.
From 4 to 4 dash.
Yes. For 4 to 4 dash, but continuously for how many times? This fluid should continue to evaporate. For how long? That depends upon the flight time. So I can find out this mass which should be taken, which should be carried for that flight. Okay, so all the basic fundamentals of thermodynamics, heat transfers we are using here to design these practical applications. Okay. This q dot is clear. This q dot is this part. This is the heat which we want to remove. Okay. And we want to find out m of that fluid, not of air. Air m dot is different. Here the m of that fluid. So m of that fluid, HFG of that fluid which is evaporating, divided by time. That is explained here also. Mass of evaporator required to be carried for the given flight time. Okay, that is that equation. Here is the T. This is m dot of air. This air is flowing in that system. What is this Q? This Q and this Q are different. What is this Q? This one, m dots from 5 to 6 or 5 dash to 6. This is Q, the refrigeration load. What is this Q? E, that is only for this part. This is represented as QE, Q evaporative. Okay, to calculate m of E. And this is m of air. Okay, this is m of E in kilograms. This is m dot of air. Here it should be m dot because it is kilograms per hour.
So QE should be given or temperature.
We can calculate how much we want to reduce the temperature from here to here.
So
If I know the delta T, I can find out QE, m dot Cp delta T. Okay. Okay, so let's do one numerical related to this one. A simple evaporative air conditioning, air refrigeration system, which we just saw, is used for an aeroplane to take 20 tons of refrigeration load, right? Q is given. The ambient air conditions are 20 and 0.9. So, okay, its solution is here. I will explain directly from there. So, let's number it. That is very important. 1, 2, 3, 4, 5, 6, 7.
isn't it for dash or 12?
Okay, we will see if dash is required, we'll put dash. Okay. And also let's draw its TS. The ambient air conditions are 20 and 0.9. So this is P1, this is 0.1. So this P1 and T1 are given. Okay. The ambient air is rammed isentropically to a pressure of 1 bar. Ramming 1 to 2. Isentropically, no dash. The air leaving the main compressor, now it enters into the main compressor. The air leaving the main compressor, this P3, is how much? 3.5 bars. Okay. Now it is first cooled in a heat exchanger, having effectiveness of 0.6. So some more calculations are involved here. Okay. And then in the evaporator, where its temperature is reduced by, it means from here further, okay, let's name 3, 3 to 4, 4 to 5, 4 to 5. This 4 to 5 temperature difference is given, 5. Temperature is dropped by 5. Now the air from the evaporator is passed through a cooling turbine. Now it is entering into a cooling turbine, so there will be an isentropic expansion to this. Where is it? The air from the is passed through a cooling turbine, and then it is supplied to a cabin, which is to be maintained at a temperature of 25 and pressure. So this is cooling turbine 6, then 6 to 7. 0.7 data is given. This one. cabin, which is to be maintained at a temperature of 25 and pressure of 1.05. So this T7 is given and P7 is given. T6 is not given. Okay.
Isn't it same as P7?
Yes, pressure is same. There is no mention that pressure is dropping. In the previous question we saw there was pressure drop was given. Here pressure drop is not given. Here what is given here, some more things like effectiveness of a heat exchanger is given, and also the isentropic efficiency of compressor and turbine. So it means dashes will come. This compressor process is not 2 to 3, it is actually 3 dash. Similarly, turbine, it's not 5 to 6, it is 6 dash. Now finally the description of the problem is completed. So better in the exam to show all these values here, right here, P1 this much, T1 this much, whatever is given, write it here. Or separately, it's up to you, P1 is equal to this, T1 is equal to this, or whatever you like. Okay. Okay, I will solve. The solution is here. I will do it in the tutorial class. I will complete it. Okay, here is the second TS diagram. He is not using 4 and then he is using 4 dash. 1, 2, 3, 4. Now he is not using 5. He is saying calling it 4 dash in after evaporator. And then 4 dash to 5. This is isentropic. Actual point is 5 dash. Similarly, in the compressor, at the exit of compressor, actual point is not 3, it's 3 dash. Then it's 5 dash to 6. This is the cabin. You can use any other notations, it's up to you, of course. Okay, so now once this is done, now it's easy to solve. Easier to solve, not easy. A little easy. Okay, so we'll see.
We will only solve the problem, Victor. We will only solve the problem.
I do not know. We'll see.